Hi everybody, and welcome back to class number 23 of Physics 218. So a few things. So this is a Monday class. Ordinarily, as you know, we would have a homework quiz on Mondays. I don't think I want to have the paper shuffle of an actual homework quiz now, but what I would like to try for this class is to have a self-diagnostic. So I'll post that to Sakai, but what I'd like you to do is sometime as part of your work today, take 10 minutes to try to solve that self-diagnostic question as though it were part of a homework quiz. And then you can check your work against my solutions, but there'll be no grade associated with that. So last time, right, we had a lot of big ideas. We talked about the Schrödinger equation for a free particle when there's no potential energy. We saw how, for a free particle, the Schrödinger equation admits plane wave solutions, complex plane wave solutions. And we talked about how these are wave functions that have a definite wavelength, and therefore, according to de Broglie, have a definite momentum. However, because a plane wave extends all over all of space, this can't represent a localized particle. We then talked about wave packets, so how you can get something that is localized by taking a continuous sum or integral of plane waves. And then our explorations with wave packets led us to the Heisenberg uncertainty principle, namely that there's a relationship between the spread in position and the spread in momentum of a given wave function. Today, what I'd like to do is the following. I'd like to continue our discussion of wave packets. We're going to introduce the idea of phase and group velocity, which is probably something that is going to be new for all of us. I probably didn't talk about waves where the difference matters in 217. And then we'll talk a little bit about dispersion relations. Now, before we dive into new material, though, I do want us to think about an exercise that shows how the Heisenberg uncertainty principle can be useful for making order of magnitude exercises. So please take a few minutes to think about the following, and then we'll come back and discuss it. So, this exercise asked us to estimate the range of speeds one might find for a proton that's confined to the nucleus of an atom using a one-dimensional model. So the key here is treating this one-dimensionally and applying the Heisenberg uncertainty principle. So the uncertainty principle, if we're making an order of magnitude estimate, I'm just going to take the greater than or equals to as just approximately equals to. So that gives us delta x, delta px, and I'll just write approximately h bar over 2. Now, here's the thing, right? We're told that the proton is confined to the nucleus, and we're told how big the nucleus is. So I can think of this delta x as roughly the size of a nucleus. And then if we apply the definition of momentum, I can think about this as equal to the mass m of my proton times the range or spread in speeds, which I'll just call that delta v, And it's okay to be a little bit sloppy here since we're making an order of magnitude estimate. Since we know we know m and we're trying to find delta v, we can go ahead and use this and solve for delta v. And that gives us, right, we have delta x times m delta v equals h bar over 2, or delta v equals h bar over 2 m delta x. Plugging in the values we were given, you can look up what h bar is, and that's 1.05 times 10 to the minus 34 joule seconds. We know the proton mass, 1.67 times 10 to the minus 27 kilograms, and we were told the size of the nucleus, that was 4 times 10 to the minus 15 meters, and if you go and plug and chug that, the result I end up with is delta V equals 7.9 times 10 to the 6 meters per second. Okay, so the next thing that I want to look at is phase velocity. So what this is it's the answer to how fast does a given point, so for instance a crest, on a sinusoidal plane wave move. And just to be clear, we're going to be thinking about this in terms of the complex wave functions we've been talking about, even though this still applies to real waves, like things waves on a string, or things like water waves, as we'll see in an example later on today. But just for now, let's think about our plane wave function e to the e to the I k x minus omega t. So there's several ways you can go about thinking of this. You probably in 217 went and drew graphs of displacement versus position at a fixed time, and then drew the same graph at later times. You might have even drawn graphs of displacement versus time at a fixed position. So this kind of logic we'll be using here. But maybe the best way to think about this is the following. So let's look at x equals 0, t equals 0. Right? If you look at that position x equals 0 and t equals 0, well, all of this goes away, right? All of this goes away. You get e to the 0, right? So psi of 0, 0 equals a, right? So which you can think of as a crest, right? Right. The idea is that you'll still have a crest, or this crest occurs wherever this argument, I times the quantity kx minus omega t equals 0, or whenever and if you're more comfortable thinking about this in the context of something like sine kx minus omega t, that's perfectly okay. But so whenever kx minus omega t equals 0. So now, right, we want to think about, well, where, at what position does that crest happen at time t? So, at time t, crest is at, right? I can just solve this for x. So I have x equals omega t divided by k, right? Or, right, I can sort of rewrite this in a suggestive way, right? X equals something times t, well, that's constant velocity motion, right? So this here is exactly how fast a given crest moves. So this is our phase velocity. Phase velocity. And I'll define that as v. I'll write v p sub ph for now. So v p phase. Sometimes I might get sloppy and just write v sub p. That's defined as omega divided by k. So, as it turns out, though, wave packets don't move at the phase velocity. Now, this is not at all obvious from what we talked about last time. I'm going to now cut to a PhET simulation of a moving wave packet. We do know how individual plane waves change in time, and we could work out that out mathematically, although the result just isn't very pretty. So we'll look at an animation, and I'll also link to a non-PhET animation in the slides so that you can see what's going on, even if you can't run Java-based PhETs. So, hi everybody. So we're going to take a look at this quantum tunneling in wave packets PhET to see how wave packets move. So we're probably going to revisit this PhET later on in the course, but here are some things that I want to just change right now. We want to look at a free particle, so I'm going to change this to constant, and then the potential energy is 0, so that really is our free particle. So it's going to turn out that I'm going to want to look at both either the real or the imaginary part, so I can see individual crests and troughs, as well as the magnitude of the wave function. So two other things. I'm just going to zoom in a little bit here. So I'm just going to, I'm going to zoom in there. Zoom in there. I'm going to make the initial wave packet a little bit wider so it's easier to see what's going on. All right, so we have right here's the real part. I could just as well look at the imaginary part and its crests and troughs, right? The whole wave function is complex here, we have to remember. And then, so here's our probability density, psi modulus squared. Okay, so let's first see what happens when we let this start going. So notice that the wave packet both moves and spreads out. I'll play that again. And you should play with this and explore some of the different settings. Notice that the shape of the wave packet is getting wider as time goes on. So this spreading happens to be because the phase velocity and the group velocity are not the same. So there is an important thing I want to look at in terms of the group and the phase velocity. I claimed, or we're going to claim that the group and phase velocities are different, and we can see that if we pay attention to both the shape of the wave packet, given either by the magnitude or the magnitude squared, modulus squared down here, and individual crests and troughs, so in red. So let's watch what happens with the wave packet when, let's say, like this central crest here moves over one box. So something like that. Maybe I'll give it advance it just a little bit more. So you can see that when this crest here has advanced just about one box, the overall shape of the wave packet has advanced about 2 boxes. And so we can see that the group velocity, which is the speed at which this wave packet is moving, is not the same as the phase velocity. In fact, as we'll show, it's about twice. It is twice the phase velocity. So hopefully what you notice from the PhET is that the envelope of the wave packet itself actually moves faster than the individual crests and troughs. So they go faster. The envelope goes faster. So it turns out wave packets move at a speed at what's called the group velocity. So V group, which I'll write V sub g, turns out to be defined as d omega d k. Now, the proof of this is discussed in Townsend. I'm going to make probably another video that's sort of an appendix to this class where I'll go through the proof. It's not a proof that I would probably go through in class if I were live with you, because it's kind of long and detailed, but since we're doing videos anyway, it won't be. I'll go and make sort of a supplementary, optional video you can watch if you want to see me go through the proof of this relationship. Let's think about what the group and phase velocity are like for both light waves and quantum waves. Oh, before I do that, I knew I was forgetting something. One other thing I need to define is the mathematical relationship So it turns out, since we care about both like omega divided by k and d omega dk, right? Omega as a function of k. So let me just note that. So omega as a function, the angular frequency is a function of wave number, is called a dispersion relation. And we'll talk about in a second why that's a good name. Is a dispersion. To help us get a better understanding of what's going on here, I'd like to compare a type of wave you're very familiar with, light, to this new wave that we're thinking about, matter waves, so free particle solutions to the Schrodinger equation. So we're going to compare them in sort of three different ways. The dispersion relationship, omega is a function of k, the phase velocity, omega over k, and the group velocity, d omega dk. So let's first start off with light. So you can show from like the sinusoidal relationship, the fundamental relation for sinusoidal waves, that light satisfies omega equals c k. And I think that might have actually been part of the homework, one or two homeworks ago. Now, if we have this function of omega is a function of k here, well, calculating the phase velocity is just a matter of dividing by k. So for light, v phase is ck divided by k, or just c, where c is the speed of light. We can also calculate the group velocity. So v group is ddk ck, but the derivative of a constant times something is just that constant, right? So this also ends up being c. So the takeaway is that for light, Vg equals v phase. And that's why you probably didn't dwell on or talk about phase versus group velocity in 217, because there's no meaningful difference between them. What this means is that if I have a wave packet made out of light, it's always going to go just as fast as the individual crests and troughs. So this is what's something that we call a non-dispersive wave. Now, a few things here. One thing that I want to mention is, why is this called a dispersion relation? You've probably talked about dispersion in the context of light when you've looked at light propagating through materials. So if you think about, let's say, how a prism works because light travels at different speeds depending on its wavelength as it goes through a material like glass. And so you get like optical dispersion if c is not a constant, right? If c is not a constant and instead depended on wavelength, or k, right? If c were a function of k, then this argument we went through here doesn't hold up, and you wouldn't get the fact that the phase and group velocities were the same. And so that's where the term dispersion relation comes from, and that's also the sort of physical origin of optical dispersion. Now, let's think about what happens for quantum matter waves. So remember in the last class we said that in order to be a solution of the Schrodinger equation for a free particle, we have to have h bar omega equals h bar squared k squared over 2m. What this means is that we can solve for omega, and that means that omega is h bar k squared over 2m. So now we can calculate the phase velocity here. So from this, v phase, if I divide this expression by k, I get h bar k over 2m. So already we can see why this might be a little bit of an issue, this phase velocity, right? So h bar k is momentum, and so momentum divided by m should be v, and so if we just look at the phase velocity, it kind of suggests that we've got something that's moving half as fast as mv, as its momentum would suggest, which doesn't quite make sense. We're rescued when we think about the group velocity, because if we calculate d omega dk here, so h bar, when I take the derivative of k squared, I get a factor of 2, and that knocks out the factor of 2 in the denominator here, and that gives us v group equals h bar k over m, right? So, right, we said, right, that that a wave packet can represent a particle in the sense that it's localized, and we've seen that the wave packet moves at h bar k over m, so consistent. So this is consistent with particle moving with velocity p over m. And so that's why we care about the difference between the group and the phase velocity for these matter waves. Unlike water waves, these are dispersive because we have this quadratic dispersion relationship here. Also notice that the group velocity is twice the phase velocity. If you go back and look at that Fed again, I think you can maybe convince yourself that that's plausible or at least consistent with watching the motion of the wave packet versus the motion of the individual crests and troughs. I'd now like to have you look at an example where we think about a wave that does have a different kind of dispersion relation, namely a water wave in deep water. We're not going to go through the the fluid dynamics of why this is the right dispersion relation for water waves, but if you take that as a given, you can calculate some interesting things about water waves, and then we'll come back and discuss some of the implications at the end.